what are these Navier-Stokes equations? Now these are those 5 equations which we have already talked about. So they are actually traditionally known as Navier-Stokes equations. Okay. And what are those equations? They are basically the same we have discussed. One is continuity equation, 3 momentum equations, and 1 energy equation. They all put together are called Navier-Stokes equation. Now we have already discussed how to derive them. The issue before us is now how to solve them. Okay. So if we look at these equations, you will find that there are certain parameters like tau ij which form part of these equations. Okay. And these are about 9 of them, total 9 of them. Okay. So what we have to see that before we are going to solve these equations, we have to check that the number of unknowns shall be equal to the number of equations, because unless until you have a parity between the two, number of equations and number of unknowns, you cannot solve a set of equations. That's a general rule of mathematics. Okay. So when we look at these equations, what happens that the number of variables are much more. There are many variables, and you can look at what these variables are. You can if we look at these equations, these are our momentum equations. You can see that if you see the variables here, one is rho, u, v, w. Okay. Then you talk about P, pressure, and we talk about tau ij, and they are total 9. Okay. Rho, u, v, p, and tau ij. Now this is a external parameter fx, fy, and fz. They are external parameters, so they will be given. So they are not unknown, they are body forces. So we have to know what is the field there which is supplying the body force. So we don't have to bother about them as far as unknown is concerned. Okay. We can also look at the energy equation. Yes. Apart from that, you will find that what we have discussed above, we can rewrite them: rho, u, v, w, tau ij, p. Now you have one variable here E and one variable here T, additional. Okay, K is there, but K is again a property. Okay. So how many variables are there? Again, you can say that Q dot S, this is a rate of production of heat per unit volume within the control volume. This is also given from outside. Either you will know from the chemical reaction or some other thing. Okay. X, Y, Z and T, they are coordinates, so we don't have to bother about them. Now if you look at them, how many equations are there, unknowns are there? You have 1, 2, 3, 4 and 9, 13, 14, 15 and 16. And the number of equations are 5. Obviously we cannot solve them. So we have to go back and see what we can do about it. So now when this problem came up, Stokes gave a solution that for Newtonian fluids, what he did was he converted these variables by one variable which is a property of the fluid. So all these tau ij, which are 9, so we had total 16. From there, if 9 are gone, you are left with 7. Okay, so we will talk about the other later on, that how we are going to handle them. But at least from 16 we are going to come to 7. So what he is saying is, Stokes is saying that these tau ij, they can be written as a function of property of fluid. Okay, and this is whole article is about that how do we replace tau ij with the property of fluid. Okay, so as a result, what will happen? 9 variables will be going. Now Stokes equations are basically used for aerodynamic problems only. What he is giving is for the aerodynamic problem and for Newtonian fluids, right? So your water and your air is Newtonian fluid. What is a Newtonian fluid? Newtonian fluid is one in which shear stress is proportional to the time rate of strain. In other words, it is the velocity gradients. They are called Newtonian fluids. So when this shear stress is proportional to time rate of strain, okay, and what is strain? I told you that if you want to find out strain, you take we talk about 2D, let us say. We talk about a shape and this is deformed like this, right? Now this distance is called, if you have x and y like this is x and this is y, this is called delta x, okay, and this distance is called delta y, and here the strain is called delta x by delta y. Okay, this is the strain and it is a dimensionless quantity. Now if you find the derivative of this strain, what will happen? This derivative will be of this x, which will be, it will become velocity. So basically it's talking about rate of change of velocity, or rather I shouldn't use the word rate because rate is term used with when you are finding derivative with respect to time. So is, you can say, the change of velocity with respect to distance, and that is gradient. Okay, if you are finding the derivative or the changes with respect to distance or the dimension, any dimension in distance, it is called, it's a one component of gradient. We have talked about it. So we can say that this stress is proportional to velocity gradients. Okay. So for example, there is a fluid like blood which is a non-Newtonian fluid. For a non-Newtonian fluid, what will happen? The stress is not proportional to the velocity gradient. This is what will happen. Okay. So it becomes clear now that we are talking only about Newtonian fluids, which mean air and water. Now if we have to go for other fluids, what we will do? We'll have to look for similar equations for tau. In some cases tau may be constant also, right? But you have to specify tau some way or the other, maybe some function of time, velocity, temperature, whatever it is. These are the parameters which have to be supplied, which are the characteristic or the property of fluid. We should know it. We are talking about stresses. Stress is the property of fluid. Okay. Now, in aerodynamics, for all cases you can assume that it's a Newtonian fluid, and therefore you can use this Stokes equation. And I told you that this whole exercise was done in 1845. So we are roughly about 180 years. Now you would recall that when I told you in the first class or probably the second class that fluid dynamics is a very old branch. Almost in the beginning of when the science was developing, they have come up. The problem at that time was the computer was not available, and that is why they could not solve because the problem at that time was you cannot solve the differential equation. They knew the solution, how to solve it, numerical solution, but they didn't have the numerical power. Okay, so when it came, computers came, immediately people started working on this. And as computers developed, similarly CFD branch has developed. Okay. So what are these equations? These are you can say total, we may even say 9 equations for 9 stresses: tau xx, tau yy and tau zz. When we talk about normal stresses, it is given like this: lambda divergence of velocity plus 2 mu into del u by del x. Okay. Same for all of them. You can remember them just by rotation, you can get it. Okay. So instead of remembering them individually, remember one and try to rotate it. Okay. Now if you look at this equation, you can see this is same in all of them. So this will come as it is. What is changing here is, say this, del u by del x. So this is nothing but Vx and this is x. This is Vy by y, Vz by z. So when you are talking about tau zz, it is derivative of velocity in z direction with respect to z. Okay. Now similarly, when you talk about tau xy, we know that tau xy is equal to tau yx. We will talk about it subsequently. So these 6 can be put together in 3 equations. Okay. And here also you can see that this is Vy and this is Vx. So it's a pair. When you have a y velocity at the top, you have x at the bottom. When you have x velocity at the top, you have y at the bottom. Okay, same thing. Now there are two variables we are using here, or two properties rather, lambda and mu. Now mu is called the coefficient of molecular viscosity. Now what is the molecular viscosity? Molecular viscosity is because of random motion of the molecules. Okay, you are not imparting anything else. So whenever you have a fluid or you have a fluid, I mean you gas or liquid, you know those molecules, they are not fixed in their place. This is the basic difference between solid and a fluid. Right? If you have a solid, right, and there is one particular atom here, whatever you do, it will remain here only. It will slightly change its place, slightly, it will remain here, and all the neighboring will remain same. So solid has this characteristic that its neighbor remains same. It's hand holding them. So all of them are hand holding. So whatever there are atoms around a particular atom, they will remain the same. This is the character of solid. So there is nothing like diffusion here. Of course, solids have their diffusion, like electron diffusion is there, or diffusion of impurities are there, on which basically your semiconductors work. But as far as the nucleus is concerned, electrons may diffuse because electrons are free. They can move from one atom to another, to another, to another. But the nucleus is fixed with its neighbors. That is what is solid. But when you talk about liquid, or for that matter air, you take any atom here, it can travel any direction on its own. It doesn't have to take others along. It is attracted by them, but it is not bound to them. We can move freely. So now these atoms, when they move, they carry energy and momentum with them, right? And that leads to, because whenever there is a shifting of momentum, it will lead to exchange of force. Rate of change of momentum is force. So shear stress or other stress will come into play. So this is the molecular viscosity, which is because of the diffusion of the molecules. Okay. Then there is another lambda, which is called the second viscosity. I'll tell you about it sometime later on. But Stokes made an hypothesis that lambda is equal to minus 2 by 3 mu. Why he is doing it? Because now lambda will also be replaced, and mu, we very well know what is mu experimentally, right? So you will find that in all these equations, lambda and mu are there, and u and v and w, which are there already, they are already counted, so they do not add up to variables. They are not the extra variables. U can be there 10 times, it is not 10 variables, it is only one variable. Okay, so tau have gone and u, v, w, lambda and w have, so lambda and mu have come. And once you say that lambda is a function of mu, again your lambda is also gone. And mu is a property of the fluid. So again that is known before. So all tau i's are gone. Okay. Now this hypothesis is frequently used in aerodynamics, but it has still not been confirmed. So I have to check this, what is the status of this. I read Anderson book, this is from Anderson book, and this is what he says, that this hypothesis has not been proved. Okay. Now then there is another thing we talked about, that tau xy is equal to tau yx. All these shear stresses come in pair and they are equal and opposite to the other. Now the reason being that is that there is a more fundamental law here, that this symmetry between shear forces stresses is necessary to ensure that angular velocity of the fluid element does not become infinite as its volume shrinks to zero. Now if it is not so, what will happen, that if you reduce the size of the cell, there will be difference between the two forces and it will lead to infinite angular velocity, which is not possible, right? So from that we conclude that these three are same. So what we have done, using 6 equation you have replaced all the 9. Okay. Now what we have to do, we have to substitute these equations, Stokes equation, to the conservative form of conservation of momentum equation. So we will talk about first conservation of momentum equation, and there we will substitute. These are the 3 equations, momentum equation, and we intend to replace these 9 terms. Okay. And this is what we are talking about. We have written equations for all of them. So we will write equations, substitute the value of them here. Now what we have done here is basically this, if you talk about this equation, this is one term and this is actually 3 terms. Okay. And they have written like this, because you multiply this V is 3 components, you will multiply with this, you will get UU, UV, UW, right? And then you will do the divergence, that means del by del x, del by del y, del by del z. So you will get this UU, UV, UW, del x, del y, del z. So we just written them in a okay. Now what we are doing is, here the right side has these terms. This is the tau xx term inside the bracket, tau yy term and tau zz term. Okay, and we have replaced it using Stokes equation. Same thing for y direction and same thing for z direction. Okay. So you can say you have got these equations, these are the momentum equation, and you can see them, there is no tau here. Okay, you have pressure, you have rho u v w tau ij, sorry tau ij's are not there, and pressure. ये रिप्लेस हो जाता है यहाँ से, प्रेशर. ठीक है. Now let us talk about the energy equation. This is our energy equation. Now these are tau ij terms. Okay. And we have to replace them. Now what we have done, we have only talking about this. It's difficult to write the whole equation again and again. It's better to identify the term, go term by term. Otherwise, when you write too many times, you might make a mistake. Okay. So this is broken into, this term is broken into 9 components. These are A, B, C and so on. Okay. Nothing special, we are just putting I as ijk or xyz and j as again xyz. Okay, and you get this. Now what we do here is we also substitute this tau xy is equal to tau yx. So these are the 9 terms. What we have done is, we have, I think x, y, yx is there something. Okay, what we will do, we will write this. What we will do, we will x, y and yx, they will be taken as tau xy. Similarly, you have this yz and zy here. So this is what we will do. So another, they can be combined. If you do that, what we have done, we have brought these terms together, xx, yy, zz, tau xy, tau yz and tau zx. We have brought them together. Okay. Now tau xx we know. So we will multiply it by del u by del x. So a term is tau xx multiplied by del u by del x, and this will become, you will multiply this by del u by del x, this as well as this. So this becomes lambda del u square by del x, and all these terms will be there. Same thing we will do for B, A, B, C, D, E, the second term, E, that is tau yy, and you do this. Okay. Then you do it for Z, ZZ, and you get this term. And now you add them up all. So when you add A, E and I, you get 3 these terms, and then you get these 6 of these terms, 1, 2, 3 into 2, 6 terms, and then you have 3 of these square terms. You see this, these are the square terms here. This term is w by z. It should have been wz here. This is wz square here. You have v by y square, that is here, and these terms, if you look at this, yes, lambda del W by del Z. This is coming here, and these two terms are coming in this. So, and then you can combine these two terms also, and you get this square. So what we have done is written like this. ठीक है, ये जो है हमारा ये बदल गया. ठीक है. Now we talk about these terms B, D, F, H, G, C. Total 9. 3 we have already covered. 6 are left here. Okay. Now, so we know that tau ij is written like this. So when you add up B plus D, they will come like this. Okay. B plus D will come like this and this. Okay. Right. So you have made a pair like this, B plus D like this, FH here, GC here. Okay. Because what will be D here actually? Tau Ix. So you have one term of tau xy, the second term of tau yx. You can combine them, you can get this. Okay. Now then you can, tau xy is actually mu into this only. So you become square of this. So each terms become square of this, mu into square of this, mu into square of this. So this is what you get. So those 9 terms have been included like this. Okay. Okay, so we were here. These 9 terms have been taken care of. Now, what we have done, this is our energy equation. We have put those shear work terms here, all of them. 9 terms we have replaced. This is what we have got. Now, you can count this. Now you will find rho, density UVW, and pressure also here. Pressure will also be here because you see this. Yeah, pressure is, where do you have pressure? Energy mean here. This is the pressure here. अच्छा हाँ, ये this is pressure. Okay. Okay. Now E and T are basically same, because E is talking about internal energy, which is a function of temperature. So wherever you have E, E will be actually rho CVT. Rho is constant. Of course, rho is already existing. CV is constant. T से मल्टीप्लाई कर देंगे, rho CVT आ जाए. ये जो प्रेशर वाली इक्वेशन है वो P इज इक्वल टू रो आर टी, ये आपकी इक्वेशन ऐड हो जाएगी, गैस इक्वेशन और सम अदर स्टेट इक्वेशन, सो दैट यू हैव नाउ 6 इक्वेशन, 6 अननोन्स, 6 इक्वेशन. So this is makes it complete. So this is what we do. Okay. So the whole exercise is about that. What we have done is we have replaced tau ij by velocity gradients, right? But the problem still remains that what about non-Newtonian fluids? These relations does not exist for non-Newtonian fluids. So we'll have to think about it. We are now doing it because otherwise what will I will get confused. Okay? So you have to be careful. Okay. Now you can close this file and the next topic we wish to cover is boundary conditions. Now another interesting thing you will find that in CFD, that these Navier-Stokes equations are always same. Whatever the problem is, if you are using Newtonian fluids, right? So whether it is suppose we talk about air, so whether it is the wings of the aeroplane, or it is a flow through some tunnel, through pipes, or a swinging of a ball, right? Everywhere you will find the equations are same. But how come then the results are different? Equations are same, right? In each problem, how come then we get the result for different cases? Okay, take this example. If if you are having this a wing, the fluid is flowing here, you have a ball, right? In one case your body is like this, in the other case body is like this, right? And there could be other shape also you can have. Okay, how come we get using the same equation? Because nowhere we have talked about the equation. Navier-Stokes equations are simple mathematics, physics. How come our results come differently? So the actual thing is that boundary conditions boundary conditions and the initial conditions, they dictate a particular solution. What is the boundary? That determines what will be the result or the initial condition. So what is your domain? Your domain is space domain. If you talk about space domain will be what? You'll have x, something like that, x, y and z, some domain is there, and time t1 to t2, this is initial condition and this is final condition. So your result is going to depend upon what are your boundaries and what is your initial condition. They will determine that. So the change comes from there. So let me yes. Let us take a case, right? Now you take a simple domain like this. Right? And some fluid is entering here. Right? And it is exiting from here. Now we make a grid here. Okay. We take another condition here. This is, let us say, V1 and V2. Now you consider this cell, one cell this, and another cell is this one. I call this as cell A and this cell as B. Okay. Now as far as cell A is concerned, it is in two different cases, it is facing two different velocities. But when the B is concerned, B is only replying to what is A doing. Right? So for B, no equations are changing. What is changing is what the A is doing. Similarly for A also, what the A is doing is governed by those equations, but what is changing A in two cases is the inlet condition. So on this left surface, what is happening, that is changing, and that thing gets propagated throughout. So the effect, so in CFD what actually happens is, the first effect is felt on the boundaries. If you look at the solution, right, the way you proceed, because you start solving the equations from one end to another. So if you are actually solving this, right, how will you solve? You will start from here, go like this, and go like this, and so on. One by one you will solving this. So what is happening is, the effect which is felt on the boundary is propagated downward. So slowly and slowly the changes what has occurred on the inlet, on the initial boundaries or at the inlet, they are transferred to the other cell. Every cell is behaving with the same equation. Only thing what has happened, at some places something has changed, which now getting reflected slowly and slowly. So is something like that. If I keep a heater here, okay, after some time you will start feeling that you're feeling hotness. Okay, if I remove the heater, after some time you will find that it has become normal. So slowly the effect passes on. But the conductivity equation remains same. Convection and conductivity, their laws remain same. So these your equations, Navier-Stokes equations, are actually representing the physical laws: continuity, momentum, an inertia equation. Those laws are not going to change. What changes is the condition on which it is. So this is, so the whole thing becomes important is, that is what is your, you can say, boundary conditions. So the first boundary condition is no slip. I would like to finish this topic here. Another 5-10 minutes it will take. Okay. What is a no slip condition? As the name suggests, when the relative velocity between the surface and the fluid immediately next to the surface is 0, it is called no slip. Relative velocity, not the actual velocity. So if something is moving and the air is moving with that body, then it is a no slip condition. Okay. So at the boundary, if your surface is stationary, that means it's at any point. If suppose your surface is like this, and it is stationary, at a point its velocities are u, v, w, they are 0, and because the fluid is in touch with it and there is no relative velocity, its velocity will also be 0. So u, v, w will be equal to at the boundary only. So if you take a no slip condition, it will be velocity. Take the example of this room. The air next to the wall immediately will be stationary, but here in the room the air is flowing. Okay. So at the boundary we can put the condition as no slip. Second, fluid temperature is equal to the wall temperature. The wall and the fluid are in contact and they are having the same temperature. This is you can say, this is analogous to no slip condition. So what is happening? There is no temperature difference between the surface and the fluid immediately. So you can say T is equal to TW. So you know what is the wall temperature, okay, and you know what is the fluid temperature because they are same. So suppose it's a hot wall and you know the temperature of the wall, you can say that the temperature of the air just next to the wall is same as that of the wall. So this is the, you can also have a case in which heat flux is known at the boundary. You might be able to find out that there is a vessel and some heat is flowing in it. What is the rate of heat flow? And you know that it is equal, the equation is minus K delta T by del N at the wall. So if you note the heat flow, you can write this equation, or you can write here that this will become the condition. Del T by del N at the wall is equal to minus QW by K. Same equation written differently. This is telling us what is the gradient of temperature at the wall. This is the heat flux and this is the thermal conductivity, and you get relation between the two. Now what is N here? N here is a vector normal to the surface. Okay. So we have, because it's not necessary that our surface is horizontal. If surface is horizontal, you will say this is our del T by del X, del Y. Okay. But surface is like this. Let us say your surface is like this. Then when we are talking about del T by del N, this is n vector, okay, and then it can be anything, I, j, k, or combination of that, whatever it is. So we are talking in terms of normal to the surface, okay. Then if it is an adiabatic wall, what will happen? Heat flow across the wall is zero, simple, del T by del N at the wall will be equal. So if you are talking about adiabatic wall, you have to give this condition at the boundary, okay. Then if your wall is non-porous, non-porous means nothing is flowing in. If nothing is flowing in, that means this velocity is equal to 0. This is your wall. It is non-porous, that means nothing can flow across this. This is not possible. What does it mean? V is 0. So what you say, V dot n is equal to 0. This is the nth direction. This vector is n direction. Velocity normal to the surface when it is 0, then it is non-porous. Nothing can flow in. But if velocity tangential to this is 0, then it is no slip condition. Okay? So you have to remember this. There may be a case where it is porous but no slip, or otherwise it is non-porous and there is a slip. You have to take care of that. So these are two different things. One is your tangential velocity and one is your normal velocity, okay. This tells you porosity or no porosity. This tells you slip or no slip, okay. And tangential is with respect to the surface, normal is with respect to the surface, okay. Then inflow and outflow boundaries. So whenever you have a some chamber, most of the case something will be going out, something will be coming in. So inflow will be there, outflow will be there. So you have those boundaries, inflows and outflow. So when you have flow through ducts, okay, the boundary condition pertaining to the inlet and exit of the duct are defined as inflow and outflow condition. So if you have a duct like this and you want to flow, so this is inflow and this is outflow. You have to define what are the conditions here, because you don't know before that what is there. You have to inlet conditions, you have to tell. Okay? Once you know the inlet condition, you have also to tell that what is governing the outlet condition. What is the pressure outside? Suppose I want to blow something. I am blowing into a chamber. If there is already a pressure inside, I will not be able to blow, or the flow will be low. So what is the back pressure here? That will determine how much flow will take place. So that is the outflow condition. So outflow, normally you tell the back pressure. What is the pressure outside? It could be simple atmosphere, you are blowing into the atmosphere through a pipe. Exhaust, motorcycle exhaust. What is the exhaust condition? The outflow condition. Outflow condition is simple atmospheric pressure. Right? So you have to decide what is your inlet condition, what is your outlet condition. Okay. At the inlet boundaries, we may specify the certain properties of the fluid such as velocity, pressure, temperature. You have to tell that what is the velocity, what is the temperature, because all these things are important. These you don't know. Your job starts after the inlet. The CFD starts after the inlet. Your domain starts from the inlet. So you have to decide what is coming at the inlet. Okay. वही जो है अंदर जाके रेप्लिकेट होगा, क्योंकि वो डिटरमिन करेगा, जो बाउंड्री सेल्स हैं उसकी कंडीशंस डिटरमिन करेगा. ओके, इसी तरीके से व्हाट इज एट द आउटलेट यू हैव टू डिसाइड. ओके, then there is something called free stream boundary. Now what happens is that sometimes your body is like a closed body and the fluid is around it, just like aeroplanes. Aeroplanes are flying in open atmosphere. Ships or submarines are flying in water. There is your fluid is your air and water, but air is unlimited, water is unlimited. Now the problem is that if you take whole of air as your domain becomes too big. How do you decide? Because I know the problem is, this is my wing, and I know the flow is taking place on this. I know the boundaries of the wing, but how far this air is here, on this side, on this side, on this side, how far the air I should take? It's too big, and you will not be able to solve the problem if you go for very large domain. So what we do, we hypothetically or by our own experience, we create a zone about here. There is nothing like this, no boundaries like this, we create. What are those boundaries? They are decided on the basis of the experience. What does it say? That how do you decide these boundaries? Is the effect of this body will not be felt here. So far away, after a certain time, you will not feel, right? If you stand by side on the side of a road, a vehicle goes there, you feel it. Forget about the sound. Let's, for the time being, forget about the sound. Forget about the vibration also that you feel from the ground. When you stand close to the road, there will be a impact of air flow. आपके पास पफ आएगा कोई एक, ठीक है? जैसे ही कोई गाड़ी आएगी, एक हवा का झोंका आपको फील होगा. जैसे जैसे आप दूर जाते जाओगे, आपको पता नहीं चलेगा. थोड़ी देर के बाद वो इफेक्ट आना बंद हो जाएगा. तो देयर इज अ डिस्टेंस बियॉन्ड विच the effect is not felt. Similarly, on all the sides, you will find that it's something like that. You can say that if somebody is moving away from you, is moving in the air, after certain distance you will not be able to feel its effect in terms of the flow parameters. Not that you can see it visually that it is moving. No, we are not talking about that. Pressure, volume, temperature, right? Something else. Suppose even in this room, at that point somebody has put the heater and I am sitting here, I may not feel it, right? If you do away with the radiation part, because radiation can come, or even radiation will not be felt sometimes. Take the case of a furnace. You stand close to a furnace, you feel heat is there. Go still away, you will feel it is less. You go still far away, there is no heat. Why? Because now you are feeling that whatever you are feeling otherwise also it is same. The normal temperature, whether the furnace is there or not, you are feeling the same temperature. That means there is a zone beyond which the effect of the body is not propagated. That is called the free stream boundary. And this is decided on the basis of your experience. So you know that if this is the case, this is the velocity, and you decide the boundaries there. And then what are the conditions on these boundaries? Again you have to decide what are the conditions on these boundaries. These conditions are free stream. Because that whatever the temperature is here, same is the temperature here. Whatever is the velocity here, same is the velocity here. Whatever is the density here, so same is the density here. So you decide a boundary based on your experience, which is called a free stream boundary, and the properties on that boundaries are same as that of free stream, as if the body is not there. Okay, so this is what you do. So this is your free stream boundary. ठीक है? तो this is how you decide about various okay, this is based on experience. So the thing is, let us summarize this. We have started with the differential equations, governing equations. Now we cannot solve those equations analytically, so we have to find the numerical procedure for that. Now when we are about to solve those equations, we find that number of variables are more than the number of equations, then so we have to look for the other equation. We apply Stokes equation in a particular case of Newtonian flow and convert all of them unknowns to normal already existing one, so that is reduced. Now then we realize that whatever the case is, if the fluid is same, equations will remain same. That means if the fluid is same in all situations, your result should be same, but that is not the case. Why it is not the case is because of boundary conditions. Okay, so what we see that what are the different types of boundary conditions. So not only about this equation, when we solve the CFD problem, we have to talk about boundary conditions also. Okay, and these are the typical examples of boundary conditions. Okay. So we will stop here.